It is 9 o'clock, so let's get started here. So project number 1 is due now at noon on Tuesday. I decided to move it back one day because going through the principal component analysis stuff a little bit slower than I anticipated. So I wanted to at least give you a class period, in this case Monday, to ask last minute questions if you have them regarding the project. We will finish up principal component analysis today and start factor analysis. Do note that I will not be on campus on Thursday and Friday. However, if you do have questions, please feel free to post them to the listserv or email me. I just might take me a little bit longer than usual to get back to you. Are there any questions before we begin today? Yes.
I have a question for letter F.
Good. Could we wait on that because I plan to talk about number 2 a little bit later? Okay. Sorry to do that. It's just I was hoping to get through the goblet data set example and then discuss maybe a little bit more in detail 2A through F. And if you have a question, ask it. Yes.
Do you want our R code to look like it does in your notes, or do you want our R code to be such that you could just copy it and submit it to the console?
I wanted to look at it. I wanted to look as it does in the notes. The way that I approach the grading is that I will, look at your code with the output inside of it, and if I see some incorrect answers or if I see something that's unusual, that's when I will start copying and pasting code into R.
Okay.
Okay. So it's easier for me, for grading purposes, to see everything all together. Even though it makes it more difficult in the end, eventually, if I do have to run your code. Other questions? Okay. So we left off last time about page 32, talking about this goblet data set. We found that 2 principal components accounts for about 87% of the total variation in the data. Again, think of variation in terms of its information that our data provides us. And 87% is pretty good. And I would, generally speaking, go with 2 principal components in this situation. But if you did want to, you could look at 3 principal components. You can get up to 95% of the total variation in your data. And so what I'm going to show you are some of the results with if you were to go with 2 or 3 principal components. Also, we've already talked about interpretations of these principal components. The first principal component represents kind of an overall measurement of the goblet size, you could say. Principal component number 2 is basically a contrast between the cup size and the base size. And principal component number 3 is some kind of contrast where it's a little bit more difficult to interpret. So the next step then in a principal component analysis is to come up with the principal component scores. So we've done this well already with a serial data set, so I'm going to go through the details of how to do it rather quickly. If you remember the way that R finds these principal component scores, it's not exactly the way that we would want it. So what I'm going to do is calculate the standard deviations for each of the variables in the goblet data set and put these standard deviations into the scale component of the resulting object that comes about through using printcomp. And we called that object pca.core earlier in the code. Just a little warning, something I came across when I was writing lecture notes actually yesterday, and I couldn't figure out at first why I was getting odd results. Notice what I'm doing here. I'm specifying columns 2 through 6 of my goblet data set. It's just a quick way to say I want all the standard deviations of columns 2 through 6. But you have to be very careful here. You need to make sure then that the variables that you specify in the print comp here is in the exact same order. So W1 has to be basically column 2. W2 has to be column 3, and so on. The reason being is because when R actually executes print comp, it again calculates these biased standard deviations, and it puts them in the same order into the scale component of PCA.core as you have specified here in terms of order of the variables. So if these variables are a different order than what actually is in your data set that you use at this point, you're going to get wrong scores. And that was actually happening to me yesterday when I was writing up some lecture notes. Unfortunately, it took me a half hour to figure that out. But hopefully you can learn from my mistake. Okay, so then I use the predict function to find the scores. Here are the first 6 scores, or scores for the 6 observations, I should say. Here's for the principal component number 1, number 2, and so on. Okay. Let's do some plotting of these scores so that we can make better sense of them and also of the data set in general. So the first thing that I'm going to do is use the par function, where I'm going to say PTY equal S. You remember that means I want a square plot. The reason why I want a square plot is because I'm going to make sure my x-axis and my y-axis are exactly the same length. On my y-axis, I'm going to put principal component number 2, the scores. And then on the x-axis, I'm going to put principal component number 1. Now remember that principal component number 1 should have more variation than principal component number 2. So by putting everything on axes that are exactly the same length will help me see that additional variability. So to make sure that I do have everything the same length, what I'm going to do is find exactly the same limits for my x-axis and y-axis. And the way I do that is simply finding the minimum of the principal component number 1 and number 2 scores. And then also I do the maximum of those same scores as well. I plot principal component number 1 again on the x-axis, y-axis, principal component number 2. I put some nice labels on the plot. And you can see how I use the common dot limits then for x-lim and y-lim. And of course I put some nice grid lines. I'm going to put some horizontal vertical lines on the plots at 0 in terms of the x and y axis so that I can better see when I have a negative or positive principal component score. And then lastly, this text function is going to plot at principal component number 1 and principal component number 2 plus 2. It's going to plot the observation numbers to help me identify which observations correspond to which plotting point. And this is what I come up with. Okay. So, to help make sense of this plot, let's look at a plot that we've already seen before before we did the principal component analysis. I don't think that a split screen here will work very well, so I'm not going to do split screen, but on page 29 of the notes, you can see back to the goblet, goblet star plot. Okay. Now you will remember when we looked at that star plot, we said number 4, 5, and 17 all seem to be really big altogether in comparison to the other goblets. And so if we had some kind of grouping, if we want to do some kind of grouping of these goblets, it might make sense to group these together. Well, take a look at then where 4, 5, and 17 then appear on our plot. They are kind of off, separated from the other goblets. Also look at what the value is for principal component number 1. Large. Remember what principal component number 1 is representing based upon what we saw for those loadings. And we said principal component number 1 is kind of an overall size measurement, or I guess we actually even said overall width, partially overall width measurement of those goblets. Now look at the star plot for number 23 and 24. We saw that W1 and W2 were large for that, meaning it had a very large cup size. But the base was very, very small. Well, look where 24 and 23, or I shouldn't say necessarily really small, but it is kind of small. Kind of is a statistical term, sure. So 24 and 23, look where they are on our principal component plot. Notice principal component number 2 is large relative to the other goblets, representing this large cup or top size of our goblets. Then we also see some other goblets that are kind of maybe all together over there too, on the left side, meaning that they're not necessarily large in comparison to the other goblets. So again, that might represent a possible grouping. For example, in the stars plot, look at, for example, number 14, number 15, number 13. And we saw in those stars plots that we kind of had small overall sizes to the star, the rays coming out. Well, now look at principal component number 1 for 13, 14, and 15. It has a small principal component number 1 score. So again, the purpose of doing this is to help relate what you see with the principal component analysis to what we had seen previously with the star plot. Also allows us to see potential groupings. Are there any questions about the plot? Okay. Now let's add a third dimension here. Well, let me back up a second. So by viewing the data like this, what you're doing is taking a 5-dimensional data set, so we have 5 variables, and you're looking at what essentially is an approximation in 2 dimensions. And depending upon how you say, how you define best approximation, one could say this is actually the best approximation in 2 dimensions of a 5-dimensional data set. Kind of an interesting way to think about what we're doing here. Now let's add a 3rd dimension to this approximation. And so now we're going to start plotting principal component number 3, the corresponding scores. And we're going to do this, first of all, with a bubble plot. Now, remember, well, also I'm going to make principal component number 3 the size of the bubble. Okay? Now that size has to be greater than or equal to 0. Otherwise, R is going to create an error. And these principal components will always be somewhere, some scores will be less than 0, some will be greater than 0. So what I'm going to need to do is adjust principal component number 3 scores so they're all positive. And the way that I can do that is find, well, what is the minimum value for principal component number 3? It's negative 1.25 in our data set. And then simply what I'm going to do is create an object called PC3.positive, meaning it's always going to be greater than or equal to 0. Note that little small change right there. It's always going to be greater than or equal to 0. And so what I'm going to do is I'm going to take the scores that are stored in score.core, the third principal component, and then subtract off then this minimum score. Now the first time you see this, you might think, why am I subtracting? Well, notice what happens when I subtract. I'm going to be subtracting a negative 1.25 from every single principal component number 3 score. So if I'm subtracting a negative 1.25, that means I'm actually adding 1.25. Okay? Then to do the bubble plot, from what we've seen from the graphics section, I just use the symbols function. The bubble part's represented by the circles argument. That's where I put my PC3.positive argument, or value. I'm going to control the size of the bubbles so that the biggest one is 0.5 inches. And again, I'm going to add text to my plot to say what is the observation number, and also lines at x equals 0 and y equals 0 on the plot to help show which is positive and negative for my principal components. And here's my bubble plot. Okay. Now obviously the observations themselves are going to be in exactly the same spot as we saw before. It's just the size of the plotting point is what's different for page 34 versus page 33. But what we see here now is some differences, some more differences that are evident amongst these goblets. So we see that these goblets that we had first identified, 4, 5, and 17, we saw that they were kind of off from the other ones. And now look at their sizes of these plotting points. We're not necessarily too big. So that means principal component number 3 is not necessarily too large, if you think of them in a positive way. But look at 23 and 24. We have very large principal component number 3 values. And that's really differentiating those goblets versus, let's say, these goblets that might be right next to it. Also, if you remember, we had this large set of points over here that, we thought, well, maybe we could group those together. Well, if you take into account principal component number 3, though, you start seeing some differences. In particular, we have some smaller principal component number 3 values, and then we have some maybe larger principal component number 3 values as well. Now we can do an additional step here too that will help you view this data with a bubble plot. And that is, how about we add some color to this plot. In particular, we're going to color the plotting point corresponding to if principal component number 3 is positive or negative. I'm going to make it a red if it's a positive. I'm going to make it a blue bubble if it's a negative. Now, when I was preparing for this class, I was going through the plot that I saw on page 35, and I thought, I think I could do a little bit better than that. So there's one aspect I don't like about that plot. We'll get into the details. What I think is a better plot, and this is in my program that's online, what I think is a better plot is what's shown here. What I'm going to do is I need to create an object that contains the corresponding colors for the bubble. So I say call dot symbol gets if else. I'm going to test, is principal component number 3 positive or not, the corresponding score. If it is, assign a red value. If it's not, assign a blue value. So those are my reds and blues. Those are going to be the colors of the bubbles. Then what I'm going to do is do exactly the same code that we had before for the last bubble plot on page 34, except for I add FG, which allows me to include then the color of the bubble. Otherwise, everything's the same. Okay, and so now here, things are standing out even a little bit better than what we saw before. We see which of the bubbles correspond to positive or negative principal component number 3. And so, in particular, I guess I can't write on here. If you watch my mouse here, in particular, we can see how these down here are positive principal component number 3s, and these are negative principal component number 3s. Again, they're differentiating themselves, these goblets, which may lead to a potential grouping of the goblets. Are there any questions? Yes?
When I run the same code online, for some reason my graph is flipped, like a 5, it's on the left side. I'm not sure what is happening.
And you're doing it in R? You're doing it right there?
Studio. Yeah, right here.
I will run it in RStudio myself just to see. So I have a theory, and that is, remember that these eigenvectors are not unique. And so what could be happening is that for some reason your eigenvectors, and I would go back to the principal the loadings and look to see if they match what are in my notes. I would hope that essentially we're using R, even though it's RStudio. RStudio basically calls R. I would hope that that shouldn't change. But I'm wondering if perhaps if I'm using 32-bit, and I believe the RStudios here are set up for 64-bit, maybe perhaps there's something in there that is causing a change. But I'll check.
So kind of like that question about multiplying everything by -1.
Yeah, corresponding to the question we had last time. Yeah. I mean, overall, of course, your interpretation is going to be the same. You just need to make sure that, especially like in a test situation, that I see what your loadings are. Okay. Any other questions?
It seems like every plot you make once you set that power function for a square plot, it's going to be square.
Yeah.
In the center.
Yes, yes.
How do I get out of
Okay.
that?
Yeah, thank you for bringing that up. It's a minor detail, but maybe perhaps I didn't mention it before. First of all, if you ever want to see various, let's say, ways to control like the size of the plot and other formatting issues with the plot, look at the help for the par function. It contains a whole bunch of different, let me blow this up. It contains a whole bunch of different options that you see there. In particular, let's look at PTY. Okay, so S to generate a square plotting region, M to generate what is the default, which is maximize the space that's available to you. So what you need to do is just say par, parentheses, PTY equal, quote, M, end quote, parentheses. Other questions? Okay, let's look at a three-dimensional three-dimensional plot. So I'm going to use the RGL package as we've done before. Plot 3D is going to allow me to plot my x-axis, principal component number 1, y-axis, principal component number 2, and z-axis, principal component number 3. Does anyone remember what the type equal h does?
The height, the lines.
Yeah, it's going to basically draw the height of the lines from, let's say, a plane that's at z equals 0. Okay, so it's going to draw the height of the lines. I'm sorry, the height of where the plotting points would go. So here you see those lines. And then what I'm going to do next is add actual points. So notice how I have a add equal true here. The points are going to be colored red. So those are my points. I'm also going to add a plane at z equals 0 using the perspective 3D function. And then let's add some nice grid lines. And here's my 3D plot. Okay. So, this is essentially what telling us what the bubble plot is telling us. Just unfortunately, there's not a good way to get the observation numbers on here. But anybody know what these two red dots are representing that I'm circling with my mouse? Which goblets? Yeah, 24 and 23. How do I know that? Because they have the largest z-axis values. Let's see now. How about this point down here? Which number is that? Thank you. 10. How do I know that? Well, take a look at this. 10, although it's probably hard to see up there, has a very, very, very little dot corresponding to it. So it actually has the minimum principal component number 3 value. But also you can see, a lot of the different separations that we saw over here. So for example, here is, let me see, if you see where my mouse is, here is 4 and 17, and here is 5. Compare that to that plot over there. Notice 5 had a bigger bubble, so that's why you see this red point closer to the green plane at z equals 0. Also, you see the differences that we saw over here with respect to the red and the blue bubbles. So here are the red bubbles, and here are the blue bubbles down there. And you see some separation between them. Yes?
I was just going to say, I think they can use the X3D function as observations.
Okay. Okay. I'll look into that. I hadn't considered that before. Thank you. So that would be nice if we could add the observation numbers too. Although then I can interactively ask you questions to help make sure that you understand what a bubble plot is versus a 3D plot like this. Anyway, so again, this is helping to see the separation. One thing you have to be careful about when you're looking at this plot here is notice that for my x and y axis, these are still the same, the same axis limits from about -1 to 4. I purposely on this plot here made my z-axis, I just let R choose it for me. And notice it goes from -1 to +1. So it's not the same common limits. You could draw it with a common limits. That would be fine. I just chose not to in this particular case because it helps you see the spread of the points a little bit better. So essentially what we're doing is zooming in on this plot. But there is justification for still using common limits as well. Okay. Let me come back to my notes. One thing that I want to point out here, too, that I failed to earlier with the bubble plots or the scatter plots, is that notice the variability of the points in principal component number 1 versus principal component number 2. Let's actually go back to this. Look at the variability in the principal component number 1 direction versus principal component number 2. You see that there's more variability for principal component number 1 than 2. Well, again, this gets into what principal components represents. The first principal component is going to explain the most variance. It's going to have the largest variance of all the principal components. And you actually see that. Let's see here. On page 37, I've actually drawn some possible groupings for the data right there, kind of corresponding to our discussions that we've already had. And what we can do then, and this is begin on page at the bottom of page 37, is well, let's maybe come up with some kind of interpretations for what these goblets represent. So, for example, the red circle up there represents large and overall size goblets. The blue goblets up there are larger cups relative to the base. Green represents the smaller and overall size, since principal component number 1 is kind of small for that. And yellow is somewhat smaller cups relative to the base as well. But if you could come up with a good way to interpret principal component number 3, you can add that in there to help differentiate the green from the yellow. It's just, since I'm not a goblet expert, I don't have a good interpretation. Okay. So page 38 then. Well, what about using the covariance matrix and correlation matrix? So far, everything what we've done is on the correlation matrix. But we talked about last time that there is some justification for using the covariance matrix. Just remember, when you do that, is that some variables will have, let's say, more of an effect on the principal components than the principal component analysis than other variables will, because principal component analysis is so centered on explaining the total variation. So if we look at then the variances for each of the variables, I do that using the apply function. So I'm going to apply the var function by column to the goblet data set. We can see that, generally speaking, W2 through W5 have similar variances. W1 has a larger variance, and W6 has a much smaller variance. So what I would expect then is that W1 is going to play a bigger role for similar reasons to what we saw with the serial data when we just used the covariance matrix, if you remember that example. It's not going to be as extreme as that example, but still, there will be some effect. Now, unfortunately, there's not a good way to still use PrinComp and use the unbiased covariance matrix. Remember that discussion last time. So since there's not a good way to do it other than simply, what you could do is just simply find the eigenvectors yourself and the eigenvalues yourself and do it that way. Since I want to demonstrate how to use PrinComp in this setting, I am going to use the biased covariance matrix. So, my code's exactly the same as before, except for now I put core equal false when I call PrinComp. I'm going to put the results into an object called pca.cove. And then I'm going to do a summary of it. I don't need my Outlook open. And so let's take a look at the output here. So this 0.303 is lambda hat 1 square root. So it's the largest eigenvalue from the estimated covariance matrix, square rooted. So in other words, it's going to be the standard deviation of principal component number 1. 0.13 is the square root of lambda hat 2. Notice that principal component number 1 explains 75% of the total variation in the data. That's pretty good. If you include principal component number 2 in this, you get up to just about 90%. That's great. 3 principal components is 95%. Well, let's look at what the eigenvectors would be, which equivalently are called in principal component analysis the loadings, since they help form the linear combination. So here's the loadings for principal component number 1. So you can say this is A hat 1, that vector. And we can see that principal component number 2 has a similar interpretation to what we had saw with using the correlation matrix. It means a measurement of the overall size, essentially, of the goblet, except for W6, which I think was the height of the base. The height of the base doesn't play that much of a role. The second principal component, again, is a contrast between the cup size, or the top of the goblet, versus the bottom of the goblet. And principal component number 3, well, good luck. Come up with a good interpretation of that, unless you are a goblet expert. Page 40. Now, what you've noticed here is that the total amount of variation explained by 2 principal components is larger here using the covariance matrix than it was using the correlation matrix. Now, don't think, though, that this analysis that we're doing here is better than the one with doing it using the correlation matrix. Okay? That has nothing to do with it here, just because one has a larger percentage of variation. In order to choose between using the correlation matrix and covariance matrix, it's a matter of judgment of which you would prefer. In terms of, is it okay to allow some variables to play a bigger role than others? When measurements are done on the same scale, as in this case, it might make sense to do that. But it's up to, often like a subject matter researcher, to make that decision. Okay, so let's do some plots of the principal component scores in a very similar manner to what we did before, so I'm not going to go through the code. And we see similar things to what we've seen before, as you would expect. 4, 5, and 17 are together, 23 and 24 together. Now we have a little bit of tighter grouping of some points over there, and maybe we have a separate grouping of some points represented there. Page 41. Here's now the bubble plot. And again, this tighter grouping of points, though, you can see, though, it's kind of a mix of the larger and the smaller circles. And if you really want to take into account principal component number 3, you might want to differentiate between some of those points. We could do a similar plot with respect to that new way to do the bubble plot. Oh, that's not right. Let me actually highlight all this code and run it. Okay, so then here's on the right-hand side is the new plot of doing a bubble plot where the red is the positive, the blue is the negative of the principal component number 3s. And again, you see the differentiation between some of them there. And also we have a 3D plot 2. That's basically telling you some very similar things to what we've seen before. So I won't go through the details. Okay. Are there any questions? Yes? The same.
things.
The same.
So would you expect to get the same number if you just use the eigenfunction?
Yes, I would expect it.
And then you don't-
It depends upon, and I don't remember exactly if inside the print-comp function, if it actually uses the eigenfunction or not. That's the key. There's actually something I will mention shortly, a different way to do some of these calculations. Let me just quickly look, see if I can come up with it on the fly. Let's see now. So the function, if I remember right, the function that actually does all the calculations is something called printcomp.default. Yeah, let's see here. So we see something with vectors. So it is using the eigenfunction. So I would expect it to be the same. Are you going to tell me that it wasn't when you tried it? I don't know. I hope it's not I hope the reason is not due to 64 versus 32 bit, as I mentioned before. When I do that little investigation, I'll check it.
You said before that if you use a covariance matrix, the print comp is going to be biased versus if you just calculate it with the function.
If you're using the covariance matrix, print comp is going to use the biased covariance matrix. So the results here will be a little bit different than, for example, the way that we said in the notes. So are the signs the same for the eigenvectors?
Not necessarily.
Okay. Because so using eigen itself, that function will give you if you do the calculations as we discussed in class, using the eigenfunction, it will give you slightly different results because we're using the unbiased covariance matrix where print comp is using the bias. So I would expect small differences there. But yeah, I'll take a look at it.
On the 3D graphs,
Mm-hmm.
what stands out to the viewer is whether you're above or below plane.
Mm-hmm.
My inclination in putting these graphs together would be to have the z-axis therefore be the first principal component because it explains most of the variation in the data, and then have the minor variation, because it's really hard to see the x1, x2, you kind of
Yeah.
twist them up, and have the minor principal components be that x1.
Yeah, that's a good idea that I hadn't thought of before. Yeah, I agree with you. And perhaps that would be something that would be more emphasized, let's say, in a full semester of a graphics course about, what would be the best way to fully, represent this. I mean, when I put this together, immediately I thought, okay, well, yeah, principal component number 1. Well, let's put it on the x-axis. That makes sense because that's typically what we put first. But yeah, I see your point definitely, and that would be good. Other questions? You have a question?
So, if I understand correctly, you calculate the principal component scores based on the loading, so the eigenvectors and that kind of coefficient type way. Then what leaves me a little confused is if you have an eigenvector that's all negative or all positive, and then your measurements that you're taking are all positive, then wouldn't you expect, for example, there to be no negative principal component scores for principal component 1, for example?
Well, obviously if you're using the correlation matrix, you're essentially computing the scores on the standardized values.
Okay.
So
in that case, it's
other questions?
I have a question. So in this 3D plot, where can you identify the number of 4 and 5, 17, 18 here for this 3D plot?
How can you identify them? Well, hopefully we could use the text3D function as discussed earlier. But what I could do right now is that, based upon where I know that things are located on the bubble plot, notice how these have large principal component number 1 scores and they're kind of away from everything else. and also these scores have to be negative. So because of that, then I know that I must be looking underneath that green plane, and we see these points are kind of sticking out. And we also see that with respect to where principal component number 1, you can see the labels kind of underneath there. This is principal component number 1, and so if you look at the actual axis, the values should be large, and so that's why I know that these are 4, 5, and 17. Okay, let's move on here. Page 43. Let's say now that you went back to the archaeological site, and what do you know? There's a goblet sticking right out of the ground. You pick up the goblet, and you want to decide what the scores would be. How would you do that? Well, hopefully you would get out your, let's say, your tablet computer, and you would plug in the corresponding measurements that you've just taken, and use, for example, the predict function for that one observation now in order to get the scores. Make sure you know how to do that on your own. Okay. Some additional comments then. Suppose more than 3 principal components are needed for a principal component analysis. How could you represent these graphically? So it was nice with the goblet data set, 2 or 3 principal components were good, and we could use the various plotting techniques such as bubble plots, scatter plots to do the plotting. What would you do if more than 3 principal components would be needed?
Do the bubble plots with the color being to the 4th principal component. So you have you plot 2, you have the size be a 3rd, and the color be the 4th.
Yeah, that will be one way. I think you might have some problems that, at least in class, the way that we talked about doing that was we had a qualitative variable as that 4th. I mean, what you could do, and I hadn't even thought about this before, is that you could somehow come up with, I can't think of what the term is, but you can imagine, let's say, for very small principal component number 4 values be a dark red, and for very large principal component number 4s be, let's say, a bright yellow. And you could somehow come up with a nice little scaling between, a continuous scaling between the points. It's like if you've ever seen what's called like a heat map. And you could represent color in that manner. That will be a possibility. Heard someone also say a stars plot. I think a parallel coordinates plot would work as well. And so there are instances where, 2 or 3 principal components might not work. But suppose instead, though, you decided that you only want to look at 2D scatter plots or 3D scatter plots. And, up to 3 principal components only accounts for about maybe 50% or even less of the total variation in your data. Should you even look at those plots? What do you think? I would say yes, but you have to remember you're not necessarily accounting for all of the information in your data, so you might be missing out on some stuff. But still, you will see people look at these plots, even if the amount of variation is not as maybe as high as you want, being accounted for by 2 or 3 principal components. They'll still look at this just to get an initial look at the data to see if something's popping out. Something of interest is being found. Just again, make sure you understand you could be missing something. But it doesn't hurt to look, typically. So notice here we haven't talked about any formal inference methods at all in this section. Meaning we haven't done hypothesis tests. We haven't done confidence intervals. You might think, for example, if you're using the correlation matrix, that doing a hypothesis test like this for the eigenvalues would be of interest. I'm sure you know why I'm doing it at 1 there, why that would be of interest. But, we didn't do any hypothesis tests like this. And I really have never seen anybody do hypothesis tests like that. Well, why? Well, the reason is because this is an exploratory data analysis. We're exploring our data to come up with some initial impressions of our data. It's not formal. Typically, principal component analysis, after you do that, you're going to now approach the data with a more formal analysis of doing some other stuff, maybe some of the stuff that we're going to be doing later in this course, for example. And so that's why typically you do not see people do confidence intervals or hypothesis tests associated with this. Okay, let's briefly talk about the project some more. So if you have that, please get it out. We're going to look at problem number 2. So again, this project deals with this applicant data. We have 48 applicants, and we're measuring 15 variables on each of the applicants. And so what I want you to do is use principal component analysis to get an initial impression of the data, maybe even come up with some ideas about which applicants might be best, based upon the information available to you. I want you to always focus on using the correlation matrix for this particular problem. However, on part A, I want you to discuss the positive and negative aspects of using the covariance matrix for this data set. There is some justification for using the covariance matrix. So I want you to actually go through a discussion of it. Tell me why it could be justified. Okay, so now the rest of it's kind of going through some of the stuff like what we did with the goblet data set. First of all, determine the number of principal components needed. Okay, we've looked at various means to do this. I think actually when we use the correlation matrix, we talked about 3 methods. I want you to look at all 3 methods and actually come up with a formal decision of, well, yeah, I think 2 principal components are good because, and tell me why. Don't just say, I'm going with 2 principal components, and not tell me why. If you do that, you're not going to get full credit. Then, try to interpret the principal components. So, there's 2 levels of your interpretations. Obviously, you can say, maybe principal component number 1 is an overall measure of the applicant. Or maybe principal component number 1 is a contrast between this and this. At least give me that. But I would like you to try to go one step further and put yourself in the shoes of the people who would, let's say, maybe reviewing these applicants to come up with some better understanding what these principal components actually represent. Next, examine plots of the principal component scores in a very similar manner to what we've done, and interpret them in the context of the problem. So, we're talking about maybe potential groupings of data like with the goblet. We've talked about potential goblets that stood out from the rest. Well, apply those same methods now here to the applicant data. In particular, I want you to talk about applicant number 42 in the data set. Now, this doesn't mean that that's the only thing that you're going to talk about in your answer here is applicant number 42. If you talk about only number 42, you will not get full credit. I just want to make sure that you do include 42 in your discussion. That's why I point this out. You're not fully answering the question if you only talk about number 42. Now, suppose that you have a late applicant, and this person receives 10s for all the 15 variables. So that means that this person is really good. Really, really, really good. Okay. Through using the previous PCA results, discuss how this particular individual will compare to the other applicants. So what do you think the first thing that you're going to do then will be? Find the score for this particular person. Would you put this person in your data set and rerun the principal component analysis? No. You just find the score. Okay? So find the score. That's the first thing that you do. Now then you're going to need to do some other stuff after that. And then lastly then, if the overall goal is to find the best individuals to hire, which of the 15 criteria, where each of the 15 criteria are given equal weighting, essentially that's what we're doing with using the correlation matrix. Now, in the actual application, it may or may not be good to do. Suggest which applicants are the best. Remember that it is most desirable to score as high as possible among the 15 variables. So you need to take that into account in determining which applicants are the best. Now your answer in part E might help you forming an answer for part F.
It seems like you're also up to part C as well, by saying that whether you prefer positive, negative, close to zero.
Yeah, that will too. I just wanted to make sure that part E, where you have this perfect applicant who scores 10s on all of them, might make you think, okay, maybe I might want to find similar applicants. Those might be good too. In this part F, and this isn't clear, I want you to be working with this part F. How should I say? Work with the 48 original applicants. So this new applicant, sorry they were late, so you can't hire them. They missed the deadline. So of the original 48 applicants, answer the question for that. Yes.
So if the weight is individual, we just can add all the score, then we get a total score for each applicant.
Well, that could be a possibility, yes. But maybe you might want some that are, let's say, better in other areas, because two applicants could have, let's say, a score of 48, let's say, or let's say 140, because each score of 1 to 10, there's 15 variables. Two applicants could have a score of 140, but maybe you might want that 140 can come about different ways. Okay. The reason why I put then that equal weight there is because essentially each of the variables, since we're using a correlation matrix, each variable has an equal weight in the analysis itself. Okay. Other questions? Did this answer your question on part F?
Yeah, I was kind of thinking along the same lines as Pam. I was thinking it's truly equal weighting. You could just standardize on the variables and then add a scores, because that would give each a coefficient of 1, whereas we're not doing that easy but analysis. I get what you're saying, where you're talking about in terms of the analysis itself.
Okay. As I said, I think I mentioned when I handed this out, I am on the hiring committee for our Department of Statistics. We're looking for a new assistant professor. And, when I came across this example, I was like, that might be useful to weed out applicants then for our process. So we'll see. Maybe I will do that. Talk to me next spring when we actually start looking at applications, and I'll let you know if I do this and how it went. Okay, if there's no other questions, let's move on here. Okay. Now, one of the things that happens when you're teaching a course for the first time, or in my case, for the first time in 8 years, and you're rewriting all your lecture notes, is that you're not for sure exactly how far you're going to get and how long some stuff is going to take. And as an example of that here, I have on page 44 all the way to page 51, some additional notes that I'm essentially going to skip, and you are not responsible for. I am going to talk about it a little bit here. But all except for one small part, you're not going to be responsible for. We need to move on and get to factor analysis. Interestingly, that these were two topics on page 44 through 51 that I had talked about before in a class situation that I thought would be good to add. And what do you know? We don't have really time to talk about them. Oh well. In mathematics, there's something called singular value decomposition. And to help understand what this is, we need to understand what an orthogonal matrix is. This is the one small thing that you need to understand because we're going to use orthogonal matrices. They're going to be very important for us in our next subsection of the course called factor analysis. Please make that a little addition that's in blue to your notes. What an orthogonal matrix is essentially think of each column inside of a matrix as a vector. And these vectors, let's say, have a length of 1. And each of these vectors are orthogonal to one another. Meaning when you take one vector, multiply by another, you get 0. Okay? What ends up happening then, and you'll see this through a quick example, is that if T was an orthogonal matrix, you took the transpose of it, and took it times T again, you get the identity matrix. Also, if you took T times T prime, you get the identity matrix. So it's kind of a nice little property, and it actually is going to be very useful for us in this factor analysis section. So, a very quick example. Remember this bivariate normal distribution that we had with the data distributions and correlations section. We have found the eigenvectors corresponding to this covariance matrix. So the eigenvector for the largest eigenvalue is listed there. The eigenvector for the second largest eigenvalue is listed there. I put them in a matrix, and one can confirm if you multiply this out that T prime times T is the identity matrix. You know, just plug it into R real fast, and you can confirm that indeed that is true. Okay, so that's an orthogonal matrix that you are responsible for. What you're not responsible for then is the rest of the stuff in the section. I do just want to briefly mention it. Okay, so in mathematics there's this thing called singular value decomposition. And what this is basically a way to decompose matrices into parts. There are many, many, many different ways to decompose matrices out there. So what I mean by that is, perhaps you have a matrix D, and you want to decompose it into two parts, let's say two matrices, A and B. So you want D to be equal to A times B. Or maybe you have a D matrix, and you want to decompose it into three parts, A, B, and C. Okay, that's what I mean by matrix decomposition. And singular value decomposition is a special case, or one way to do something like this. And the reason why that this is important for principal component analysis is through this singular value decomposition framework, you can see another way for principal component analysis to come about. Essentially, the whole main point of this section is to show you that, let's say my data is in a matrix X. What we're doing with principal component analysis is that we are trying to approximate that matrix. And the best approximation comes about through using the principal component scores. And since we haven't actually defined formal notation, think of that as a matrix on the right-hand side that contains the principal component scores. But not all principal components, maybe just two, or maybe just three. So again, another way to view principal component analysis is that you have this P column matrix X, and you're looking for the best approximation of it, maybe in two dimensions, or I'm sorry, in two columns, or maybe three columns, or four columns. And so that's why, for example, I pointed out to you when we were looking at a plot such as this, that we had basically 5 variables, and the best 2 variable approximation to it is represented by your first 2 principal component scores. That's why I brought that up. Okay, so essentially singular value decomposition gives you another way to view what we do in principal component analysis by decomposing the X matrix into different parts. And lastly, then that leads into something called biplots. Biplots is a visual way, very similar to what we've already done, that allows you to see your principal component scores and also some additional information on it. You can see a biplot if you're interested on page 50. To be honest, I haven't found these plots to be that useful. I like using the plots that we've already talked about, but that could be just my personal preference. So, finally, we are done with this section. Are there any questions? Okay. Let's move on to the next section, factor analysis. Okay. Factor analysis has some similar goals to principal component analysis. Namely, you're trying to discover the true dimension of your data. Let's say you again have p-variables, but perhaps you get just as much information from those p-variables as you would, let's say, with maybe just 2 other new variables that you formed based upon your original p-variables. So that's what I mean by discovering the true dimension of your data. Also, what you hope to do is to be able to now interpret these new variables. Just like what we did with principal components, we try to interpret what they represent in the context of our original variables. Okay. So, very similar goals to principal component analysis, this factor analysis. However, the way that it goes about doing or trying to achieve these goals is somewhat different. A benefit of doing this different method, as you will see, is that it can potentially help us come up with easier interpretations of these new variables that we form in comparison to what we did with principal components. But this interpretation can come at a cost. As I say here, some side effects. Meaning that you can actually have multiple ways to interpret these new variables, depending upon how you form them. Some people don't like that. Also, you can come up with ways to develop these new variables that actually violate your underlying assumptions of your model that you were going to see, which is, of course, not good. And I'll explain those aspects when we get to them. Also, principal component analysis, as you saw, was very, very concerned about total variation. Factor analysis is concerned about total variation as well, but also the covariances. That's going to be very important, explaining the covariance structure, not just the variance structure. Okay. Now, please note that there's going to be a lot of terminology in this section. Don't blame me. Just realize that, people who do factor analysis, they have certain terminology that they use to describe stuff, and I will use that terminology. This means then that you need to get used to it. What I've often told my students in the past is just simply, write out, all these terms that we're going to be using. Write it out on a sheet of paper, define them, and then even bring that sheet of paper to class so that when I say something called a common factor or a specific variance, and it doesn't immediately ring a bell about what that represents, you can look at your sheet of paper and figure out what it is. Okay, so here is the classical way that factor analysis is usually explained. It comes about through the very first person who conceived this idea, a guy named Spearman. I have heard of his name popping up in various places in statistics before. Way back in 1904, he was thinking about this stuff. And this is what he said. Suppose that we have a student, and they're taking some classes, in particular 6 different classes. Obviously, they were not a stat student, but they were taking the classes of classes called classics, French, music, and I forget what some of the other ones were. Okay, and they're taking these classes, and they're having tests in these classes, and we're looking at ways that we can explain how their test scores came about. And so what Spearman did was he formed some equations as kind of to hypothesize about how these test scores could have came about. So he said the classic score comes about through some constant lambda 1. Let me get a thinner pen here. The classics test score comes about through having some kind of constant, let's call it lambda 1, multiply it by some other value, let's call it f, plus another value, we'll call it eta 1. So if you knew lambda 1, if you knew f, if you knew eta 1, you would get the classic score that they have on their test. For French, lambda 2 times, oh, look at this, the same f, plus now eta 2. So you see that all these test scores have something in common. You could call this, let's say, a common factor. And what Spearman said is that this common factor could represent, let's say, the overall intelligence level of the student. So you would think that the overall intelligence level of the student plays a role of how they're going to do on a test. It's not going to be a perfect predictor, but it should play some kind of role. How much of a role is dependent upon the corresponding coefficients on F, these lambdas. These lambdas are going to have a familiar name to us. They're going to be called loadings. These are not they are not components of an eigenvector. They are not eigenvalues. They just typically, in a factor analysis setting, they're called the same thing because notice we're essentially taking up, they're essentially coefficients on these other common factors. Similar to principal component analysis where we had coefficients on our original variables. Okay. And also Spearman said that how one does on each of these tests is probably going to be also controlled by class-specific factors. Maybe, for example, a student likes taking a French class more than they like music. So in that setting, maybe the eta will be different. So these are called specific factors. Forgot to get my notes out. Take a look. Make sure I'm talking about everything I need to. Okay. Now, these lambdas are going to be stuff that we want to estimate. The F's are going to be random variables. The etas are going to be random variables as well. So you can kind of think of this as in a regression model setting. It's not a regression model, but you can kind of think of it as a regression model where we have some kind of outcome and we're hypothesizing how this outcome comes about through a nice little equation. What also makes this a little bit more difficult than regression analysis is F and the etas, you can't measure them. They're unmeasurable random variables. Some people might like to call them latent random variables. So notice in a regular old regression model setting, your independent variables, your explanatory variables, whatever you want to call them, often represented by your x's, they are measurable. You can go out and take a sample and get your x's. Here, you can't go out and take a sample and get your f's or your etas. That makes this problem more difficult. And it kind of makes sense. Then we think of them as variables, unmeasurable random variables. These f's. If f was truly, let's say, your overall intelligence level, that might be difficult to measure. Some people might say, well, go take an IQ test, but really, to some respect, you can't measure it directly. Let's see here. So, what we have just seen is what's called a factor analysis model. Because notice how I used the words factors to describe F. That's called a common factor, common to all the variables, or common to all the tests or all the classes. We have these specific factors that are specific to a particular class or test. So that's how this name factor analysis model comes about. Okay. So let's talk about this now more formally. And again, you can kind of think of this in terms of a regression model. Now here's our old regression model that all of you have seen before, where we have p variables. The x's are independent variables. They are measurable. For each observation, you have an epsilon, and that's specific to that particular observation. And what tells you what kind of role that the x's play in coming up with y are these coefficients, these betas. Okay? Now, here's what our factor analysis model looks like. We're going to be interested in coming up with a model for x. X is going to be a p by 1 vector. You can think of x as containing those test scores, for example, classics, French, and music. And we're looking at how do these x's come about. We have a hypothesized model, essentially. And we're not going to make any kind of assumption about a formal name distribution for x. Not at this time. Eventually, we will have to make a multivariate normal distribution assumption. But at least when we write out the model right now, before we worry about estimation of stuff, we don't need to make any kind of assumption, other than the fact that a mean vector exists, a covariance matrix exists for x. So this is how x comes about. Let's look at x1. You take the mean, and you're going to add a lambda 1, 1. It's going to be a coefficient, or what we're going to call a loading, on the first common factor. If lambda 1, 1 was 0, that says that this first common factor has no role in getting x1. If lambda 1 was positive, it says it has a positive role. If it's negative, it says it has a negative role. Then we have now a second loading, lambda 1, 2. Notice the indices here. Notice what's remaining 1 as I'm moving across the equation. Lambda 1, 2 is the loading corresponding to factor 2. So in that Spearmint example, we only had one common factor. Well, you could have more than one common factor. In fact, you could have up to, let's say, m common factors. Similar to what we saw with principal component analysis, we hope, in principal component analysis, we're hoping to have just a few principal components. Here, we're hoping to have just a few common factors. So you want m to be less than p. Then for every original variable, we're going to have a specific factor called eta. So that's how x1 comes about. That's our model. x2 comes about in a very similar way, but notice how these lambdas change. Again, notice the first subscript matches what was on x2. But we're still going to have these common factors that correspond to how these original variables come about. Okay. These common factors, we're going to say that they are IID, means 0, variance 1. If you haven't seen the abbreviation IID before, that's a common thing that we use in statistics to mean they're independent. So F1 is independent of F2, it's independent of F3. So they're independent random variables. The second I and the D there means identically distributed, meaning they each have the same distribution to them. They have a mean of 0 and a variance of 1. Okay? These are unmeasurable, or you can say unobservable random variables. We're not going to be able to go out and take a sample and obtain them. The etas, again, are called specific factors. They are all independent of one another. That's a model assumption with a mean of 0 and a variance of psi sub j. So notice here, we have a j subscript on the eta, we have a j subscript on the psi. So that means, potentially, each of these etas have potentially a different variance. These psi's are called the specific variance of eta. Kind of makes sense. If we have specific factors, we have then a variance associated with it called a specific variance. Also in our model, we're going to assume that the F's and the etas are all independent. So what happens with the common factors has no effect on the specific factors. It's a model assumption. And then lastly, these lambdas are called factor loadings. Most people just call them factor loadings. I guess more specifically, they'd be called common factor loadings, but most people just call them factor loadings. Again, these lambdas are not eigenvalue. They are not They are not parts of eigenvectors either. Okay, we are out of time. Are there any questions? Okay, then that's it for today.